talk in our afternoon session today on domain theory will be given by Keye Martin, and he's going to tell us about domain theory and causal structure.
All right, thanks. I just wanted to say, for some of you might know, I went to the doctor yesterday and they gave me some medicine, so I could very well sort of pass out in the middle of this talk, and if that doesn't happen, my voice might go out. So for that reason, I want to try to go as fast as I can to finish. So, are there any questions? Thank you. All right. So seriously, before I start, I want to just say this. I'm looking right now for undergraduate students and graduate students, postdocs, other people interested in research, money, and research. And funding workshops and conferences. And I mean, that's not an all-inclusive list. I'm just trying to give you an idea. Everything's welcome. You know, send an email to me. That's my email. I just wanted to say that. Many of you have received emails from me begging for you to send me people that I can give money to, and you've sent me no one.
So, Scott Cowan?
Right. That's all I meant. So, please. You know.
How about a Navy-funded Belarus workshop?
That sounds like a really good idea. Except maybe we can move it to like the South Pacific. So this is an outline of the talk. I'm going to tell you about domains and measurement, which is pretty easy to explain. Like Prakash already said, domains offer you a qualitative view of information, and measurement offers you, one of the things it offers you is a quantitative view. And we're going to ask some weird questions like, what is the information content of a space-time interval? Right? Is there a relation between information content and geometry? And Prakash showed you how to construct space-time as a space, all right, as a manifold, meaning just topologically. But there's another question here, which is like, when you do that, can you also construct its geometry, meaning its Lorentz metric, right? Because this is a completely separate thing. I mean, pretty much the way I look at it now is they're almost just like opposites. You know, it's just this other structure that's sort of there with it, right? So I just wanted to tell you two really quick things. So this is information qualitatively, right? In a domain, you have a set of informative objects with an order on it called the information order. And if you write x below y, it means that x carries information about y, right? See? So you can think of y as being more precise, but that's what it means. Right? X carries information about y. Now this approximation relation with you saw, beat to death, right, in the last talk, means not only that X carries information about Y, but that it carries essential information about Y. This is like the new way that I like to say this because it's very brief and it cuts through all the crap. Just say it like that, right? And what I mean by essential is that not only does X carry information about Y, but it also carries information about any process that tends to Y. You see what I mean? Right? So you can carry information about Y without carrying information about all processes that tend to Y. So I just wanted to remind you of these two basic facts about domains, because they'll be sort of important. Now, here's what we're going to try to do now. So in my thesis, which was about computation, I basically asked the question, well, if a domain is a collection of informative objects, right, and the order is telling you something about information in a qualitative way, right, how could you actually say what it meant to measure the amount of information in something, right? Now, we weren't looking for like an absolute, definition of information content, but we were looking for a strong property that measures of information content usually had. Do you see what I mean? If we could, we'd define information content perfectly, right? But instead, it was just like, let's find a property that it has, right, in many contexts. So we began with this idea, and it went like this, all right? You have some function on a domain, and it's going to assign a number to every element of the domain, which measures the amount of information in the object. Now, the amount of information could be like how partial the element is, or how uncertain it is, all right? And there are two things that were really simple. These are called measurements, by the way. But when you move up in the order, see, uncertainty should decrease, right? Right? Things become less partial as you move up. Right? This is very easy to think. Just think of the example you already saw, like with space-time intervals. If you have a space-time interval that looks like this, right? And then you have a single point, for instance, right? The one that looks like this is much more partial, right, than the point. And it's in the following sense. If somebody tells you, a signal was sent from P to Q, right, the larger the diamond, the more uncertain you are about the path it took. You see what I mean? And as it shrinks, you somehow gain more certainty about it. That's the intuition. For us, the ability to measure information content will always have these properties, right? Which we call Scott continuity. Right? But this is actually like just the tip, really, of the iceberg. The definitive property that separates any Scott continuous map, all right, which for us will be one like this, is that it measures the domain. And I'm going to actually explain this. I never explained this. The reason I never explain this condition is that basically I just usually don't care about the audience that I'm talking to. But I really like everybody.
We love you too, Keye.
Yeah. No, I said usually, but I'm going to explain it today because I like everybody here. So, all right. So the idea is, and this is it. It's a one-way implication. If we had a measure of information content, what properties might it have? All right. It's not an if and only if, right? Because we don't want to get into that because you're crazy, right? But if we had one, all right. Well, it would be Scott continuous. That's the first one. But the second one is this property here. And I want to explain this. So let me do that. So first imagine that all we care about is computation. There's something that we want to compute, right? And its name is x. So there, right? We want to compute this thing. Now remember, this whole thing, the whole view in the study of domains and measurement is that the qualitative and the quantitative are not like these separate disjoint disciplines. Do you know what I mean? Like, we don't look at the universe as sort of like, well, those people do differential equations, and we like categories, and we hate each other, so, right? It's not, they're intertwined. So, we want to compute this thing, and it's an ideal object, right? It's perfect, right? So, we say we would like to calculate it to within an accuracy of A. So, how do we write that down, right? We say to within. So that's step one, to within an accuracy of A. Okay? That's the first thing. Okay? Now then, what happens? We use some process, like say an iterative algorithm, right? And the algorithm computes, right? So the algorithm, what does it give us? It gives us many, it's iterative. So it gives us many xn's, okay? Right? And they're all below x, meaning they all carry information about x, right? All right, so it gives us that. And then our question is, like, how do we know that we achieve this accuracy? First, actually, what does it mean to achieve accuracy? So let's write, that's step 3. We have achieved accuracy A, right? See, accuracy A, when this happens. You see? When A carries essential information about X. All right. Now then the big question, and this is the one we really care about, how do we, the human, know? Like, how do we know that we achieved this? You see? And so how do we know? So let's actually put this in here. How do we know? How do we know when 3 happens? You see? And at this point, actually, let me show you what's in my head, in case it's not what's in your head. So, I take some variable and I set it to be 0, and then I increment it, okay? And then I compute the first term, and then I iterate. And when do I do it? See, everybody knows this. You do it until you're close enough, right? So what does close enough mean? So let's write this down. It means when this thing is like within an epsilon, right? When we achieve within an epsilon, this loop stops and we go xn is the desired accuracy. That's what we're thinking of over here. So you just sort of have that in the back of your head. Anyway, how do you know when it happens? All right, well, so the answer is because, all right, some mu, which is a measure of information content, we're not going to call it that. Just some mu, some measure of accuracy, tells you that there is some tolerance, okay, right? And so, and that has, and So there is some tolerance, right? Where if you have any term in here, right, then and they're close enough, you see, in information, right? So you have this, right? So there is some tolerance, and they're close enough in accuracy, then it tells you that you've actually achieved what you set out to achieve. See, I'm paraphrasing. If I want to be very precise, by the way, right, here's what I should write, right? And like, actually, let me add it, because I do want to be precise. So I want to say, you see, I left this off because obviously we already know that this is true, right, from up here, right? But I'm putting it in now, right? So it's going to tell you there is some accuracy, right, where, and actually, you know what? We don't even need this either. Let's write it like this. I'll write it like this. Yeah, that's better. See? Oh wait, sorry. This and this. What does this mean? Right? So how do we know when we've achieved this accuracy? Right? We're looking at this loop. It says, well, because there is some epsilon, right, where if you look at any stage in this process, and you have something that carries information about X, and they're this close to each other, right, in information content, just put that in quotes, right, then you've actually achieved that accuracy. You see? So this is the big claim. That the claim is, if you have a function, mu, that can do that, right, not only for any process that computes X, okay? So not only for any process, but for any Y. So let's now erase the XNs, you see, and put in a Y, right? Like that, and here, right? And in addition, for any A, you see what I mean? That approximates this X, right? So for every approximation of X, there is an epsilon, so that no matter what process you follow, if your process gives you an iterate that contains information about X and is this close in information content to X, then you've actually achieved the accuracy A. You see? Because it's not enough to just say, well, it's about one process, it's about all of them. And it's not enough to say it's about one accuracy, it's about all of them. Right? That's what the measurement condition is. And the claim is, if you have a function that's powerful enough to do that, then it must be measuring the information content of the objects. Right? All right. Well, this quantification here, what does this mean? This means X is in the way opposite of A. That's what that means. Right? Well, those are a basis for the Scott topology. So you can replace them with any Scott open set. Right? And that's what this condition means. That's why, if that holds, then we say that the function mu measures the content of X, of the point X, just of that single point. So I don't know if that helps. But so the thing is, in computer science, it's very easy to find many, many examples of those. And we do all sorts of things with them, okay? I mean, for instance, once you have this idea, if you have a function on a domain, you can take its informatic derivative. And you can measure the rate at which functions on domains, like converge to fixed points. And our talk doesn't have anything in it like this, but I just want to show you how easy this is. You see? So you would do this. You would say, well, I look at the content of the output over the content of the input. This has been very useful, by the way, in studying quantum channels. Because quantum channels will turn out to be, very nice quantum channels will be Scott continuous maps, domain of quantum states. And their informatic derivatives not only exist, but they determine something called the Halevo capacity. Right? I just want to give you an example of what you do with it. Now, so here's the thing. I'm going to give you some more examples. But what's hard for me to believe is that this idea, which I fully confess was like made up when thinking about computing on a domain, it's really hard for me to believe that it shows up in so many other ways, right? And this is right in line with what Samson was talking about when he said, like, mathematical structure that's very definite, that shows up in many contexts, right? So, when you have a measurement, here are a couple things that happen. Suppose that an object has measure 0, right, then it has to be a maximal element in the order. And what does that mean? It means if it's got no uncertainty, right, then you can't improve it in the order. So what I mean? It's maximally informative. Here's another thing. Suppose that you have two comparable objects that have the same information content, then they're equal. See, it makes sense. If you have two objects and one carries information about the other, and they have the same information content, they're equal. Would it be true? See, would this statement be true if you didn't know that x was below y? No. That would make no sense at all. Right? You see, and this is what I mean. The qualitative and the quantitative interact. Right? It's not correct to say that, the information being the same would make them equal unless you first knew it was okay to compare them. Right? And then the third thing, which is very bizarre, actually, to see, is that when you have a measurement, you can recover the Scott topology. So what do? You look at these sets right here. See, these sets that I wrote down. And you look at everything that is above them. And if you do that, you get a basis for the Scott topology at any point in the domain where the thing actually measures it. So you can sit for a while and think, why is it that the ability to measure the information content of an object is somehow related to topology? Right? And really, the only reason is because when we first started off, we talked about approximation. And the Scott topology is like the topology of approximation. But other than that, there's no earthly reason why there ought to be a connection like this, between topology and information content. So here's an example. Binary channels. You've seen binary channels before. They take bits as inputs and bits as outputs, right? And either a 0 gets flipped with probability 1 minus a, or a 1 gets flipped with probability b, right? And so I want to show you 3 examples of this kind of stuff, right? One of which will be related to relativity. So you've seen these. The way we measure the amount of information that goes through a channel is with its capacity. What it measures is the maximum correlation between input sent and output received. Okay? So you get it by maximizing the mutual information. If you want, you can derive a formula for it, which is down here. Right? And so, if you think about it for a minute, it's like how I was thinking about it one day. You can imagine a domain of binary channels, right? Where what you're trying to do is measure how secure a system is, all right? And these channels are all hidden within a system. So the smaller the capacity, the more secure the system is, right? And then because of that, the more certain you are that the system's okay. So in that sense, a small capacity channel should be up at the top. Now, I'm not going to go about ordering channels, right? For a binary channel, the probability of error is that, all right? So if you look at the probability that a 0 is sent, right? If that's t, then that's the formula up there, this e thing, all right? That's the probability of an error. So it means that's the probability that either a 0 gets turned into a 1 or a 1 gets turned into a 0. And so we might say, well, let's order channels by saying that one channel is below another if the probability of error increases, no matter what distribution you send the inputs on. See? That's natural. If you do that, you get a domain that has capacity as a measurement, right? And in fact, the domain you get is actually the one that Prakash was talking about. Remember we was talking about the interval domain over the real line, right? Well, this turns out to be the interval domain, but not over the real line, just over the unit interval, right? Which is an interesting fact, but it's got a really deep consequence. It ties in to that sort of fun-sounding stuff about capacity, so I want to show it to you. Now, so here's what this means. Here's an example of what you can do when you know you have a measurement on a domain. All right? So say I have one. Now, whenever I can, you can't always, but you can always arrange this so that it works. Right? You can define a distance function on a domain. And you say, well, all right, I'll say the distance between x and y, I'll look at the things that are below both x and y and take the measure. Oh, sorry, and I'll take the infimum, like this. All right, now if I do this on the interval domain over the unit interval, all right, this actually works out to be this. Now, here's the weird thing. This distance function, it's known that its epsilon balls, right? And this is all like from the study of measurement. Its epsilon balls always give you a basis for the Scott topology, right? Don't worry, I'm going somewhere with this, right? So these always give you a basis for the Scott topology. In particular, if you take these balls and you restrict them just to the maximal elements, like this, right? Then this has to be a basis for the Scott topology on this, right? Which we know is the interval, the Euclidean topology. So what does this mean? This means anytime you have a measurement on the interval domain, right, you have a distance function that gives rise to Euclidean topology on the top. Now watch how weird this is. If for mu, we substitute capacity, which in case you forgot is this ridiculous function right here, this thing, right, then what does it mean? It means this function, right, which you can actually show, works out to be like nothing more than literally this. So let me write it out. I'll write it out as rho. We have a function like this, defined by the capacity, same as rho, right? It's symmetric, right? So I'll write it's symmetric, right? It has the property that if you take 2 points, then their distance is 0, if and only if they're equal, but no triangle inequality, right? Its epsilon balls give you a basis for the Euclidean topology. You see? Now, so what does that mean? That means that the unit interval is an example of a space where you can take 2 points, right? And given these 2 points, you can go off and you can associate a noise matrix, and then you can take its capacity, right? And you can then say that the distance between 2 points in space is the amount of information that can be transmitted between them. You see, you have to have a way to get a channel from the 2 points. But if you have it, you can do that, and you can do it in such a way that the distance function is actually capacity, and it actually gives you the Euclidean topology, and it's because of all the nonsense that I just scribbled here. That's one example of like what it means. Right? There are a lot of other things that you can do with even just this one example, right? But that's an interesting example. Now, there's another one, which I'm not going to go into at all, but you probably are not surprised to hear that there's a domain of classical states. Not just one, in fact, there are 3 of them. 3 distinct order theoretic structures, and each one corresponds to a different view of probability. Right? If you take the view that a finite probability distribution is like a continuous extension of a set, and you say, well, I want to take, inclusion of sets and extended probability distributions, you can. You get a domain with respect to which entropy is a measurement, and it works nice. If you want to take a sort of Bayesian view of probability, which is what me and Bob did, you get the same exact results. And there's a third one, which you may have heard of, majorization. Right? Majorization, if you restrict it to the states that decrease, is also a domain, and entropy there is also a measurement. They correspond to 3 different views of probability, so there's no problem there. It's not a question of like, oh, so then there's no right answer, there's no canonical structure. No, because there's no one way to look at probability, right? So the same thing happens with quantum mixed states. You have a domain of quantum mixed states that define only entropy as a measurement, and you can derive things that are just as strange in those cases, but there's no time for that. So here's an example from relativity now, a third example. These functions are real. We didn't make these up, and I just don't want to stress. The causality relation actually was in, like, Hawking's book, like way before I was born, probably, right? And we didn't invent that. We didn't invent any of this stuff. We just looked at it and went, hey, wow, this actually fits the math we're doing right now in a completely unrelated context, right? So a global time function is this, right? In essence, you look at every event in space-time, and you go, I'm going to label every event with a definitive type of time, right? I like to call this like the Newtonian view of time, right? That you can take every event, and you can say, that happened at time t. Now, formally, they have a few properties, right? They're continuous from space-time into the real life. They're strictly monotone, which you might remember measurements are, right? And the inverse image of every point is a Cauchy surface, right? So I'm not about to define what that is, but I'm going to draw a picture. So what would make sigma a Cauchy surface? So we can picture sigma as being like that, just this thing that goes on forever, okay? And think of that as all the things that happen at time t, where we're not really talking about physical time, but like a mathematician's concept of time. And what would make this a Cauchy surface is that if you took a curve that goes on forever and into the future, it would hit it in one and only one point. That's what would make it a Cauchy surface. So those are called global time functions, and their existence is actually equivalent to like, well, depending on how you define them, you know, they actually do correspond to a particular type of causality condition. Here's the theorem anyway. If you have a global time function on a globally hyperbolic spacetime, right, then you can extend it in a very natural way, right, to the domain of spacetime intervals, right? So you remember we had the domain of intervals over the real line. Well, we're just doing the same thing now with, you know, the domain of spacetime intervals. And what do? You look at the time that's been assigned to the one in the future, and you subtract from that the time assigned to it for the one in the past. It's very natural, right? When you do that, you get a function that measures the entire interval domain of spacetime intervals, right? And it's a measurement where the set of things is exactly the set of events, the maximum ones, right? So what does this mean? And here's the thing, because later I'm going to like tell you a bunch of really weird stuff about time, or you know, it'll probably sound a little bit weird. This means that from only the information order and the Newtonian concept of time, right, you can reconstruct the topology of space-time. Right? Now the reason that's interesting is because the same is not true if you replace Newtonian time with relativistic time. Right? So the physicist's definition of time. That's it. So I just want you to keep that in mind. All right. So now here's another example of a function that you might want to look at, right? This is the Lorentz distance, and this is the one we pretty much mean is the metric. Technically, a metric is used to define a length of a curve. All right, what is this function? And by the way, this just shows you like how natural all the domain theoretic structure is in relativity. Right? If you open up a book, you know, on relativity, the first thing you'll see when they define the Lorentz distance, right, which by the way is like it's the length of the maximum length geodesic that connects 2 points in space-time. Right? And those exist because you're on a globally hyperbolic space-time. But the first thing you'll see is, I'll go, well, if the 2 points joined by the curve are causally related, then the length is this nice number. Right? And if they're not causally related, then it's like, what, infinity or not defined, or it doesn't matter. It's some crap value that nobody cares about. And you see, the thing is, here, right, when we're looking for functions that are just on the interval domain, we don't have this problem. Right? Because the only things we're considering are the intervals. And the whole point is that there's a reason to consider the intervals. Right? The intervals themselves are really all you need. So anyway, that's what the Lorentz distance is. And we proved that it's Scott continuous. And so what does this mean? You know, this means that if you take one interval, like this one, right? So here's x, see? And then you take another one, right? Its monotonicity means that if you look at like the maximum geodesic from this point to this point, right? Then it's longer. See, than the one that would just like connect these 2 points. See, and intuitively you believe that, right? You know, and proving its continuity is a consequence of like what we might call its Euclidean continuity, but that's actually not easy. It's not so easy to prove this, but it is true that it's Scott continuous, right? Now, okay, what does it mean, by the way? This is what it means. If you had 2 events, and they were causally related, so, like, it could be this event and this event, what is this number? This is the amount of time that would be recorded on a clock if it traveled from one point to the other with the thing clicked. So imagine you send a signal, or even better, I don't know, imagine you were like some kind of particle that had a clock inside it that didn't weigh anything or whatever, you know, and it moved. It's the amount of time that clock would record when it went from there to there. That's what that thing measures, and it's Scott continuous, right? Now I'm going to show you what you can do with just this. So we go back to the reconstruction of space-time, where we start off with a countable dense set, right? And we have a trick in domain theory, and it's a pretty simple trick. Well, it's simple actually once somebody teaches it to you. Before then, it's probably not something you will come up with. But you start off with something called an abstract basis, and you perform its rounded ideal completion, right? An abstract basis is something that's you have a set with a relation called way below, if you like, right? It's transitive and it's interpolative, and that's usually all it is. See, so the trick that we came up with when we reconstructed space-time was, you know what we ought to do? We ought to, you got to think about this for a minute, right? We ought to take an abstract basis, and we ought to use it to define a new one, right? And the new one is actually the relation we started with in the first abstract basis. You see what I mean? That's what that says. Take an abstract basis and form a new one, which you could think of as the formal intervals over the previous one. And then to be able to do that and still get an abstract basis, you have to know something more about the one you begin with. But anyway, in this case, we happen to know what we need to know. So we form this new abstract basis, which you can think of as the formal intervals over this countable dense set. And we define its relation to be that, which looks familiar to you, right? And then we take its rounded ideal completion, so we get a domain. Then once we get this domain, we take its set of maximum elements in relative Scott topology, and provided that we begin with a countable dense set, we have reconstructed space-time as a space. All right, just topologically, that's all, right? All right, now, by the way, I want to say this one thing here. Some people will look at this and go, yes, but when do you get a manifold, right? It's not such a good question, guys, and this is why. One time you get a manifold, right, is when you start with a countable dense set. And what we're actually saying is something a little bit different. We know that the continuum is at odds with like the view of modern physics. What we're saying is whatever kind of space you ought to be working in to have a field about quantum gravity, it's contained in this construction. Certainly it needs to be refined. But actually asking the question, when do we get a manifold, is not really so important. We don't really care. I mean, we may not really care. I'll put it that way, right? All right. So that's how you reconstruct the space. Now watch how easy it is to also get the geometry at the same time, right? Which is gravity, right? That's why we care about this stuff. So we do the same thing. We begin with another countable set, except this time, right, we know we're going to be forming these formal intervals, so we begin with a countable collection of numbers. Do you see the idea starting now? It's like somebody goes, here are the fundamental events in the universe. They're whatever. They might be a countable dense set of what we today call space-time. They might be just something else, just some patch of space-time that we care about. But whatever they are, we pick them. Then once we've picked them, we pick things that we are thinking of as Lorentz distances. Whatever those are, we pick them. And we call those L sub A, B. And we pick them in such a way that they're monotone. You see, a countable set of numbers, and when you look at, and each one is assigned to a pair of points so that they're monotone. Then when we perform the reconstruction of space-time, at the exact same time, we're able to reconstruct a Scott continuous map named L, right? In the event that some person picked the countable dense set of events, right, and the countable collection of Lorentz distances, you have now constructed space-time and its geometry. Because what happens here is that this function, L, agrees with the Lorentz distance on a countable dense subset of the domain. So they have to be equal because they're both continuous. Right? So this is the point. The point is, from a countable set of events and a countable set of distances, it is possible to reconstruct the space-time manifold with its geometry in a purely autotheoretic manner. There's still this huge question, if you wanted a theory for physics, which is like, how do you restrict this construction? How do you figure out which countable sets and countable distances are talking about what we call reality, right? But don't let that blind us, to like the idea that, wait a minute, are you serious? We can actually do that? Like, yeah. And knowing that even in theory is a surprise. That's surprising to know that. All right. So anyway, the question that I avoided, which now I'm going to like address directly, right? The Lorentz distance is not a measurement. It's not continuous, but it violates the measurement property. And this is the part that I love. This is my absolute favorite thing. And Prakash will tell you when we were working on it, like I think I nearly drove us both sort of mad, right? So because I kept saying, no, there's a deep explanation, and we're not finding it. We can't just say it's not true. Like there's something there. And there is something there, right? Here's what happens, right? So first, simple explanation. Why is the Lorentz distance, though it is Scott continuous, why is it not a measurement? All right? Because remember, if you have a measurement, then anything that has measure 0 has to be maximal, right? All right, you're going to love this. And if you don't love this, it means you were sleeping and you should have had some coffee or some tea or some amphetamines. You see, you guys are sleeping, man. I'm watching like half the people in this audience sleeping. You know the standpoint? They never heard this talk. When's the last time you heard me talk? You see me like standing up here, like killing my voice. I'm going to be suffering tonight, all because of you. You don't care at all.
Keye, I stayed in bed till 12 just for you.
Did you really? That's not why you stayed in bed, man. And if you want me, unless you want me to tell them, you better shut up. All right. It's Scott continuous, right? But it's not a measurement, and I want to show you why, because this is amazing, right? I was very happy when I saw this. So look, all right. The reason that it's not a measurement is because we can have d of x equal to 0, right? But x is not a maximal element, right, in the interval domain. So we can have an interval whose measure is 0, right, but it's not maximal, right? And watch how great this is. Which one? Okay, here's the light cone. This is the future of x, right? So like right here, if we go here, okay, what kind of interval do we get? We get this interval. This is, this is a nice one, right? And does this help us? Actually, let's call this A and B, because that's going to suck if I do x1. So A and B. All right, so this interval, no, right? This thing is positive. All right, but here's the thing. What does it mean if you're in the interior of light cone? It means you can send a signal from here to here, and you don't have to travel at the speed of light. But the things on the boundary, all right? So like one right here, this one, you must travel at the speed of light. If you want to get from here to like this B, so then we're going to forget about this one. We don't care. No, this one's C. What happens here? Well, see, the Lorentz distance is, this is traveling at the speed of light. Right? How much time does a clock record if you travel from there to there at the speed of light? Right? It's one of the fundamental principles of relativity. The answer is 0. Right? Right? It's 0. Right? So we have an element that's definitely not maximal because it's not an event. Right? But its measure is 0 because a clock that travels along here doesn't record any time. You see? So what does it mean? It means that this thing, right, the Lorentz distance, can't distinguish a point, an event, from what we call a null interval. A null interval is anything whose Lorentz distance is 0. Right? All right. Now, so here's what's amazing about that. If we ask specifically now, is there a deeper reason why? Right? See, let me say it this way. Because remember, I told you, this area is about like a lot of things at once. Suppose that we're thinking of rectangles, right? X and Y. Right? That's the perimeter of a rectangle, right? And this is the area of a rectangle. Now, suppose that you want to solve two equations. Because I want to show you, I want to show you that basically computer scientists already knew this. Because what are we saying when we say that? We're saying that if you buy into domain theory's definition of what it means to measure information content, we're making the statement that the Lorentz distance itself is not a measure of information content. But to understand it, you don't even need really to look into relativity. I mean, you do because you need somebody to get the answer. But once you see it, imagine you want to solve this system of two equations, two unknowns. Right? And the way you do it, so an approximation of a solution, because the solution is a vector of 2 points, is a rectangle, right? So you imagine a sequence of rectangles that are shrinking towards an answer, right? Now, if I said to you, how do you measure the information content of a rectangle in this problem, right? If you said to me, well, you use the area, right? You wouldn't say it. And the reason is because this thing has area 0, right? So perfectly certain, supposedly, and yet all you would have done is reduce the location of the answer to a line, right? Which is like having a nonlinear equation solving one variable. You see what I mean? So my point is you wouldn't make the statement that area, right, was a measure of information content of a rectangle with respect to the problem of solving this system of equations. But perimeter you would. You see? Because perimeter, if it shrinks to 0, then you have to have a point. You see what I'm saying? So all I'm saying now is like this is global time, and this is the Lorentz distance. Or to put it another way, this is the relativistic idea of time. It's area. And this is the Newtonian idea. It's easy to understand. But the thing is, there's a deep reason. There's a deep thing that happens. And this is it. So, see, from one point of view, it looks like the Newtonian definition of time is like much nicer, right? You know, it's a measurement, right? Like they're both Scott continuous, and it's a measurement, but the Lorentz distance is not. But you can take a completely different view under which the Lorentz distance is the nicer of the two, right? And this is very hard to believe. Here's what we do. You remember the interval topology that Prakash talked about, right? Well, you can extend it from a bicontinuous poset to just any continuous poset, right? What you do is you take intervals, just like we had before, but some points don't have intervals around them, like that, so you take Scott open sets, right? And what you say is, we're interested, you know, in cases where that thing exists. Maybe it doesn't, we don't care about those. We want to know when they exist. All right, then here's what you can prove. So the first thing we already know, global time and relativistic time are both Scott continuous, right? We know this. The second thing, the Lorentz distance is interval continuous, right? But Newtonian time is not, right? The third thing is that Newtonian time is a measure of information content, but the Lorentz distance is not, right? And here's the really deep thing. Why? Like, why does some of this happen? Because if you have any interval continuous function on the domain of space-time intervals, right, then it necessarily can never measure information content. It's never possible, right? And the reason is because by interval continuity, any object which doesn't approximate anything, like this one, would always have to have measure 0. You see? So any interval continuous function will have a giant set of elements of measure 0, and will never be a measure of information content. And so it's almost, like what I'm trying to say is like, it's like one of the basic laws of relativity that the Lorentz distance does not measure information content. If by information content you mean what we mean in domain theory. And there's a very good reason to think that that is what we mean. Because, you know, we know many other examples where it works. You know, not that it's easy to prove it works, but, you know, they work. So this is this is an interesting result. Because like I said before, the first result makes it look like Lorentz distance is nicer, right? Because it's not only Scott continuous, but interval continuous. You know, but then this result makes it look like, no, Newtonian time is nicer, because it measures information content. And the truth is, I mean, there's some weird way in which they're like opposite. They're both very nice. You know what I mean? They're both very nice. But, you know, that's an interesting answer. So here's some things we learned. I always like to end the talk with what we learned. So we learned that we can reconstruct the space-time manifold with its geometry from a countable set using only order. We learned that. And we learned that you can describe the difference between the Newtonian relativistic notions of time using topology. Now, the topology of space-time? No. Okay? A very weird topology on the domain of space-time intervals, which, by the way, is never Hausdorff. Right? I didn't mention that, but the interval topology on the domain of space-time intervals is actually never Hausdorff, which is another very strange thing. And it's not the Scott topology. Right? So, yeah. Or here's another way, it's almost to say the same thing, but I wanted to point out specifically, the difference between the topology and the geometry can be described topologically. This isn't very, very difficult. Again, I mean a topology on the domain of space-time intervals. And when I use topology and geometry up front, by geometry I mean the stuff you use to describe gravity on the space-time, and by topology I just mean the manifold. Right? Like they're different, and I mean actually if you look at it physically, you wouldn't even think that we're really connected, right? There'd be no reason to think it. But you can still ask the question, how are they different, if you want. It can actually prove a thing that says they are. It's funny, you can use a weird topology to do it. And then the last thing is this. When Prakash and I were talking, like there are a lot of times, right, where he teaches me things. I ask him questions, and like, you know, I bother him with a lot of questions, right? And one day I kept going, see, I would always talk about Lorentz invariance. And Prakash, what do you mean by Lorentz invariance? And he'd say, well, in a flat space-time, blah, blah, you know, right? And we kept trying to figure out, like, what it meant, like, looking through books. What does it mean in a general space-time? And it was like, I don't know, it's only my opinion, but it seems like it's sort of an elusive idea, you know? I mean, would you agree with that? Like, if you try to locate it, nobody wants to be pinned down on what it is. But the one thing I would say is, because you remember, what's the idea here? The idea is that, yeah, you know, with a little bit of extra stuff, you may be able to recast general relativity in an order theoretic way. That's in a nutshell, you know, that's the idea. Have we done it yet? Like, hell no, we haven't done it. There's like a huge thing missing, right? There's a little thing called like the field equations. You know, oops, right? You know, no, but you know, getting the geometry, that's much more than probably anybody thought you could get, right? But the thing is, Lorentz invariance, what it's saying is if there was a way to found it on like just like the basics of order and countable sets and very non-traditional things, it would be telling you, and this is a really important thing, you probably should expect that part of the definition of a Lorentz invariant quantity, right? And I mean not only in a general relativistic sense, but like in a really wacko quantum gravity sense, is that it would be interval continuous in some way, right? And I mean, I don't know, it kind of gives me chills when I think about it. You know, but it's like I said, Newtonian time is not interval continuous, right? And relativistic time is. You know what I mean? So it's not like one's nicer than the other. They're just fundamentally different. And this fact is, you know, I mean, but that's exactly really what this is saying. Like when you make a statement like this interval can be zero, whenever it approximates nothing, right? And that means for any null interval, the time recorded by a clock that moves through it is zero. You know, that's an exciting thing to me. I mean, we learned a lot more than this. You know, but I knew that I'd go on and run out of time. So, are there any questions? Because my voice is almost shot.
There's 10 more minutes in
In that case, I guess it means like everybody here's buying me a drink for getting on early. But I don't want to pass out. My God.
Okay, I've got a question.
Yeah.
So, conceptually, you see this as that you're approximating the continuum discrete. But can you see this also as physical spacetime being some sort of emergent property out of quantum?
Yeah, that's actually how I've always looked at it. And that was part of like, I had a sort of mini rant in there when I was talking about reconstructing spacetime. That's exactly, this was like the point I was trying to make, right? I can't be completely coherent about it, but like now that the talk's over, who cares? Right? This was the point I was making. It was like, all right, what's our actual model of the universe? You know, okay, what's the idea about it? Well, it's kind of like you've got these points, just these events. All right? And by quantum mechanics, there's like no more than a countable number, let's say. All right? And then for these points, you go, well, this one like is in the future of this one or whatever. See? So you do that. So then you add like a less than. See? You add a less than right there. See? So you do that. That's the next thing you do. And then now, the new thing we know now is that, oh yeah, and whenever you add a less than, you also add what you call a length. You do that. If you've done that, then we have all the math that will show you like how to reconstruct, you know, like how it is relativity as a limit. Like the normal relativity is a limit, provided that when you do this, you choose these to be the right ones. But my point is like, who says it's got to be a countable dense subset of a normal spacetime? It might just be some weird countable set, right? You know, I mean, you would have a notion of causality, you would have a notion of distance, you'd have a countable set. And you will get a space from that stuff. You'll get one. But, you know, I don't see why it necessarily has to be a manifold. I mean, you know, if somebody gives me a physical reason why, all right, you know, but I ain't heard one yet.
But surely, it looks to us like space-time is a manifold. I mean, that's why relativity is a lot of corroboration.
Well, I mean, if you mean in a math book, yeah. You know, but I mean, honestly, that's like every time I read things about like what? That basically people think that parts of space-time are quantized. The parts of space-time themselves. Like, was it Ashtekar? Yeah, for instance, yeah. No, so that's what I'm saying. Physically, no. No, in a math book, yes.
You mean at normal length scales? It looks like a manifold.
No.
Yes, so in a sense it's a sort of test, isn't it? I mean, after all, otherwise there would seem to be what else would you expect?
Right, yes. So I think it's reasonable to expect a manifold in the Lorentz when you smooth it out.
And therefore, if that's true, then it's reasonable to understand the conditions on your original countable set that would lead to that.
I'm not sure. I mean, I don't say it's not a good problem. It's not interesting. I mean, I'd love to know the answer to it. You know what I mean? But my point was just that, I mean, okay, look, that the continuum is a problem for a lot of reasons in physics, right? And I just think that if we go, oh, well, now that we have this countable set, this way of reconstructing relativity, which we do, right? If you then go, oh, well, now let's figure out all the crap we need just to get back to continuum, that's not necessarily the right step. You know, you can ask the question and you can work on it. But I look at it from a different point of view. Like, you have this countable set and you want to reconstruct something. I just want to figure out, what do the laws of physics tell us, you know, we should be assuming here, you know?
Yes, it's not necessarily the one reconstructing something, but it's the thing you construct out of it should be like the plausible construct that we have.
But the thing I got out of your point about waking up was the fact that on the edges of the cones, there really is an order you're inferring that the Lorentz distance won't measure, because it's measure zero. You've got to go with the speed of light. So maybe that part should be left out. You shouldn't say this point here is below that point. And if you took a model that said, I will only measure from this point to things that I know are in its future, in the sense of not having to travel at the speed of light to get there, then maybe you'd have a model that was more.
But you can always get points like that. Like, you literally can't avoid it.
You will excise the light cones.
Hmm?
You will excise.
If you take the light cone to be closed, to be closed, yes. But if you don't assume that,
Yes, the interior.
so you take the interior.
Okay, but let me show you what I'm talking about. So let's do that. So then let's go like this, right? So, like this, right?
Yeah.
Right. In domain theoretically, you could do that and still model space-time, but then look what happens. Now you go in here, and you've got another null interval right here.
Well, no, I know that. No, I understand the point, and that's exactly what I'm wrestling with. Is there a way, because they sit inside, in domain theory we see that all the time, with things on the boundary where, on the square, where these points aren't way below something, so it's not a problem. But you don't see it in the interior, and I'm trying to figure out a way to.
But you really do. I mean, like those null intervals, I don't want to use the word dense, right? But, but you're not going to get rid of them. Like, it's,
No, well, the points are there, but the order is what I'm saying. You're making assumptions about the nature of the partial orders.
But that's what's funny. See, but that's what's funny. Okay, look. When I draw these points and I take this thing, we're actually using time-like causality. So we're only talking about events that you don't have to travel at light.
Right.
And what I'm saying is then when we do the completion, you derive.
That's the problem, that when you do the completion,
Yeah.
it's in exactly that point is, I think, where you're violating something.
Yeah.
But why do you want to get rid of them?
Well, I'm just trying to figure out if there's a model you can do that would.
But I think they're there and they capture an important thing. Right? I mean, for one thing, if you kept only the time-like ordering, it would emerge anyway as a closure. But more importantly, the fact is those are the things that are invariant under the Lorentz transformations.
So you have a characterization of which of these systems produce four-dimensional space-time?
No.
Isn't that exactly the question
Or that's really...
No. I'm like I said, I don't reject the question. I just say that it is not the question.
No,
It may be, I said it's interesting, I'd love to know the answer, right? But it's not the fundamental question.
Well,
story.
if you want to get beyond and try to do quantum gravity or something like that, it would certainly be helpful to see in other words, to know here are the models.
Right, that's why I'd love to know the answer.
GR,
Right.
And then, you would then look at that characterization and say, well, let's fudge it here and see what...
Right, but see, and like I said, that's why I'd love to know the answer. But on the other hand, what I'm trying to do is shift the paradigm and how people look at this. right? Because I have a feeling that if we solve that question, then all anybody would try to do is just like basically redo everything in order to, and that's it. And that's not the point of this, right? The point is like to sort of start off like with a really broad landscape where we don't know. Like it's so broad that we're pretty sure it's in there, you know what I mean? And then to restrict it based on different principles. If that makes sense.
People usually also always say quantum gravity is a motivation for this. But if you go, I'm not a big reader, but if you read Science et l'hypothèse, Science and Hypothesis of Poincaré, before quantum mechanics, before relativity, he gives a big argument that space-time should be some emergent thing. Like, I can't exactly reproduce, but space-time is not theater. It's some emergent thing from some other whatever process is going on.
Yeah, that's the idea I like.
And you don't need quantum or relativity.
Even Riemann.
Well, this is...
Riemann's inaugural lecture said that.
Huh?
Even Riemann's
Really?
inaugural lecture.
Oh.
Well,
I mean, I should have just
if you're
quoted that.
really going to go back in history, I mean, this is a relationist versus substantival, as philosophers like to call it, so Leibniz probably gets the big story.
But Poincaré came up with relativity after that. Something which the French people know that all.
Actually, I just thought about a reason why we shouldn't throw out null intervals. Because if you threw them out, like what would the Millennium Falcon do when it was running from the Empire, right, in Star Wars? Like what?
Oh my God.
What then? You know what I mean? No, we should keep them for sure. Now I'm convinced. Yeah, I know that you
I
Brits
can't
didn't
argue
get,
with that.
you Brits didn't get the Star Wars reference. You probably like Lord of the Rings people or something, but that's another story.
Shocking Pinewood Studios.
I'm not going to have a debate with you, all right? Because first of all, nobody can see you on camera, man. So, as far as they know, I won.
Let's scold the...
Go on the Citadel.